Shubho Sandhya, very good evening to all of you, respected professors, fellow researchers, my dear students, and the interested persons. Today, we are here for attending second lecture of the lecture series for propagation of statistics, education and research organized by Calcutta Statistical Association. It is a CSA outreach program to explore fundamental concepts, practical applications, and exciting advancements in the field of the statistics. This seminar aims to enhance our understanding and passion for statistical analysis. Today, Professor Manisha Pal, Professor, Department of Statistics, St. Xavier's University, and also retired Professor of Department of Statistics, University of Calcutta, will deliver her lecture on the topic network sampling for estimation in hard to reach populations. Professor Dr. Manisha Pal has taught the Department of Statistics, University of Calcutta for a period of more than 39 years. She has been the head of the department for the 2 terms and also the convener of the PhD Research Advisory Committee in the Department of Statistics, University of Calcutta for a period of 5 years. Professor Pal has visited various universities and institutions in India and abroad to deliver invited talks in different conferences, seminars, and also visited various departments for collaborative research work. She has been involved in organizing many national and international conferences and symposia. She has published almost 130 research publications in various peer-reviewed international and national journals of repute. She has served as an expert in various recruitment boards like UPSC, Staff Selection Commission, Eastern Region, Government of India, and she has been awarded the Shiksha Ratna Award by the Department of Higher Education, Government of West Bengal, and the International Distinguished Research Excellence Award 2021 in Statistics by Center for Professional Advancements of India. Madam Pal is presently the president of Calcutta Statistical Association and one of the editors of the journal Calcutta Statistical Association Bulletin and IAPQR Transactions. She is also an elected fellow of the West Bengal Academy of Science and Technology and is presently a council member of the Academy. Professor Pal is also an executive council member of Society of Statistics, Computer and Applications. Now, I am requesting Professor Pal to deliver her lecture. Madam, it's over to you.
Thank you, Shamrat, for the kind introduction. So,
Thank you.
I think I'll start now.
Yes, please.
Okay. Is my slide visible?
Yes. Can you make it full
Yes,
screen?
I'll make it slideshow only. Okay. So is it fine?
Yeah, fine.
Yes.
Absolutely.
Yes,
Okay. Okay. Good evening, everyone. So I'll be talking about estimation in hard to reach populations. As you know, for decades, statisticians have been interested in estimating the size of a finite population. We have the very well-known capture-recapture method that is frequently used. For example, suppose we want to estimate the number of fish in a pond. So in this capture-recapture method, how do we go about it? Well, firstly, through a controlled investigation, we capture some fish from the pond and we mark them and release them in the pond once again. After a certain period, we recapture fish, we count the number of marked fish in that sample, and then we equate the proportion of marked fish in the population to the proportion of marked fish in the second sample. That is m by n equal to r by t, where m denotes the total marked fish and capital N is the total population size which we want to estimate. R is the number of marked recaptured fish, and T is the total fish captured on second visit. From here, we get an estimate of the size of the fish population in the pond. Of course, there are other non-trivial methods that can be used to estimate the population size. For example, if we want a count of say the number of wild animals like tiger and leopard in any region, then a commonly used method is the pug mark technique. So the beauty of this method is that the pug mark, traces that are obtained, which forms the data. Well, from these traces, the investigator can identify the gender of, say, if we are looking at tigers, then the gender of the tiger and also the age. Now, in these methods, what happens is the population whose size we want to estimate, well, the population units, these are accessible to the investigator. Problem arises when we have a population where the units are not directly accessible to the investigator. In this case, the question is, how are we going to collect data in order to estimate the size of the population? Now, in this situation, what is generally done is that we consider another population which is closely connected to the population of interest. And the units of the second population, these are directly accessible. We call the second population the reference population. And of course, the first population is the population that we are interested in. And the units of the first population, which is not accessible, these are called the ultimate units, while the units of the reference population, these are called the reference units. Now let's look at some examples where we have situations like this. See, we could think of a mobile population, like population of tourists in resorts, then visitors in shopping centers. Then there could be a population where you have individuals having access to food coupons, which can be available through distribution centers or service centers. Then we could be interested in a population of individuals suffering from a rare disease. And these individuals, they may be visiting one or more of the diagnostic centers for treatment. So, see, if we consider the population of individuals who have access to food coupons through service centers, in this case, the reference population is the population of the service centers available. Similarly, in the third example, where individuals are suffering from a rare disease, these diagnostic centers, these together form the population of reference units. And these centers are easily accessible, and through these centers, we try to collect data about the population in which we are interested. Now, let us look at the reference units. Say, suppose there are capital M number of reference units and capital N that denotes the total number of distinct ultimate units. Now, an ultimate unit that may be connected to one or more of the reference units. And these reference units, as I have already indicated, these are easily accessible. Now this M that I am talking about, capital M, which is the total number of distinct centers, that is known to us. And in case M is not very large, then one can scan and obtain report from all these M centers and thereby obtain all the units that would be in the population of interest. That is, obtain information about the ultimate units, all the ultimate units that are connected to the reference units. In this case, of course, there's no statistical analysis to be done. However, if M is large, in this case, one has to select a sample of centers. And corresponding to these centers, they can have access to or get information about the ultimate units which are connected to the centers. Now, access will be gained to all the ultimate units through a network which is forming a bipartite digraph. So suppose these M reference units are RU1, RU2 to RUM. And let us consider first, consider a random sample of, say, a fixed size small n of reference units selected by SRSWOR. And suppose we denote the sampled RUs as RU1, RU2 to RUM. We can do it without loss of generality. Now, as I have said, that an ultimate unit may be going to or may be connected to more than one reference unit. So if I look at the first sampled reference unit, RU1, then I might find, say, some N1, small N1 ultimate units which are connected to RU1. Similarly, if I look at RU2, there will be a number of ultimate units connected to RU2. Now, the ultimate units that are connected to RU1, among them, some of them may also be connected to RU2. Similarly, for all the other sampled reference units, I can find out the ultimate units which are connected to them. In this process, we can generate a bipartite digraph which will involve the two sets, that is the reference units and the ultimate units. Now, one thing is to be noted over here is that we are selecting a random sample of reference units, but the size of the sample is fixed. So the number of selected reference units that we have at hand, that is fixed. However, because the reference units that we are selecting, well, each of these reference units may have a number of ultimate units being connected to them. Okay, and that will the number being of ultimate units that are connected, that are not known beforehand, before knowing which are the random reference units that have been selected. So the number of ultimate units that are captured in this process, that is going to be a random variable. So we can denote that by small n, and small m, that will denote the fixed number of reference units that we have selected. Let's look at a small example to understand the whole thing. See, we have capital M equal to 5 service centers, which are our reference units. So the size of the population of reference units is 5. Now, when we scan the records of all this capital M, that is 5 reference units, then we get a complete idea of the ultimate units. And in this case, we can easily calculate the total number of ultimate units in its population. And therefore, as I have indicated earlier, we do not need any statistical analysis over here. So this should be the case. Like suppose we have capital M equal to 5. So RU1, RU2 to RU5, these are the reference units. And UUJs, these are denoting the ultimate units. And as we can see, UU1 and UU2, these are connected to the reference unit RU1. Similarly, if you look at, say, UU4, so that is connected to 3 reference units like RU2, RU3, and RU4, and so on. So we have a totality of capital N equal to 8 ultimate units, and this 8 gives the size of the population of ultimate units. This is the complete network case where all the reference units have been scanned and we have obtained the ultimate units that are connected to these reference units. So we can easily get the size of the population of the ultimate units. Now, this whole thing can be represented by an incidence matrix. Like if we look at the first column, this denotes the reference units. We have 5 reference units in the population, so 1, 2 to 5. These denote the ultimate units. As we have seen in the last slide, there are 8 ultimate units. So 1, 2, 3, 4, 5, 6, 7, 8 ultimate units. Now, in the cells, this is the cell where the first reference, the first ultimate unit is connecting to the first reference unit. Well, it does happen so. Over here, as we can see, U1 is connected to RU1. So in this case, we put a 1. Similarly, the second ultimate unit, this is connected to reference unit 1. So 1 over here. And for the others, it's all 0. This way, we can, for each of the reference units, find the find these digits or input these digits 0 and 1, depending on whether the ultimate unit is connected to the reference unit or not. And if we look at these MJs, so MJs, as you understand, that is the sum of the digits in the jth column. Now, what does the first column give you? That gives you the number of reference units. That is, this is MJ is equal to 1. So this gives you the total number of reference units to which the ultimate unit 1 is connected. The second one, this 2, this gives you the total number of reference units to which the ultimate unit 2 is connected. In this way, you get these values. And if I look at Ni, so what is Ni? Ni, this N1 will be corresponding to reference unit 1. So this gives you the total number of ultimate units that are connected to the reference unit 1. And similarly for the other rows. So this gives the incidence matrix. Now let us consider the case where we are taking a sample of reference units, say by simple random sampling method without replacement. So we had capital M equal to 5 reference units. We have taken a sample of 3 reference units. Suppose these reference units are RU1, RU3, RU4. So these are RU1, RU2, RU3, and RU4. And from these reference units, we can find the ultimate units which are connected to it. As we can see, UU1 star, which is basically UU1, the first ultimate unit, that is connected over here. And it also has the second unit, which we have denoted just to indicate that it is really a sample. So we have put the star over here. So UU2 star, that is basically UU2. So these 2 units are connected to RU1. So if we go to RU3, we can find that this one, and this one, these are connected to it. and similarly for RU4. So what is the size of the sample of ultimate units? So we find it is 5. 1, 2, 3, 4, 5. So this is the sample of ultimate units that we are getting by taking a random sample of size 3 from the reference units. From this information, we can form this incidence matrix. As before, these are the reference units 1, 2, 3, 4, 5 that we have obtained over here. And these give you the incident counts. Say reference 1, the sample UU, that is ultimate unit. Well, it is connected to reference 1, so incident is 1. This value is 1, the other 0, and in this way we form the incidence matrix. This forms the data, and using this data we have to get an estimate, an acceptable estimate of the size of the population of the ultimate units. Now, generally speaking, we have this tendency to go for an unbiased estimator, but here it seems pretty difficult to get an unbiased estimator. Of course, the first attempt to this was made by Kirananandan in 1976. He found an unbiased estimator of N. That was in his thesis, which is submitted to Stanford University. From there, he got his, I'm sorry, not Stanford, from Harvard University, from where he got his PhD degree. However, subsequently, it was seen that this estimator has many flaws, like sometimes it may come out to be very large negative value. That is, the estimate of N comes out to be some very large negative value, or sometimes it may be very small, even smaller than the size of this sample of ultimate units. These were the flaws in it. But before going to the unbiased estimation of N, let us look at these two concepts, probing and no probing. Now, this probing thing, this is used in order to improve upon the data. So what do we do? What exactly is this probing? Well, as we have seen that we are taking a random sample of reference units. From the reference units, we are getting induced, ultimate units. That is the ultimate units which are connected to those reference units. Now, as I have said, an ultimate unit may be connected to more than one reference unit. So these induced ultimate units, well, from them, one may get information about other reference units which have not been sampled, but to which they are connected. That is, the investigator goes to these sampled ultimate units and request them to give information about any other reference units which have not been sampled but are connected to them, and they oblige. If they oblige, we say this is probing, and definitely here we are getting more information, and therefore our data is improved over here. Now, let's see how the incidence counts improve with probing. So this is the information before probing. These were sampled RUs. These are the induced UUs. That is the ultimate units. This is the complete network that we have bipartite diagraph. So this is the one. And well, this is the case when there's no probing. Now we have information about probing. For example, if we look at, say, UU3 star. UU3 star basically is the ultimate unit UU4. Now here in the sample, we have RUs which are connected to UU3 star. These are RU3, and RU4. But if this unit UU3 star, which as I've said is basically UU4, this unit is asked, are there any other reference units to which you are connected? Of course, and he obliges, then, I'm sorry, let me, just a minute. Yes. And he obliges, then he'll say, well, besides RU3 and RU4, I am also connected to RU2. So in this case, the incidence count is going for this U3 star will increase by 1 because he has given the information that he is also connected to RU2. That is exactly what we do. Initially, from the sample, we find the incidence count is 2 for UU3 star. But once probing is done, the incidence count goes up by 1 because the unit says that I'm also connected to RU2. So it becomes 3. Similarly, it happens for the other units, UU4 star, UU5 star. As for UU1 star, well, UU1 star is basically UU1, the first one. Now, it is connected only to RU1. So if it is asked to state any other reference unit to which it is connected, naturally it is going to say 0. So the addition is 0 over here, and the incidence count after probing remains same as before probing. So now with this probing, we are getting in more information about this ultimate units and the reference units. This is an unbiased estimator of the size of the population of ultimate units. And this is an unbiased estimator of that size, which is capital N. So here, what is MJ? MJ, this denotes the incidence count before probing. Capital MJ denotes the incidence count after probing. And capital N, that is the size, population size of the reference unit. Small m is the sample size of the reference units. And this comes out to be an unbiased estimator of the size of the population of ultimate units. In the case where m is taken to be equal to 1, one can easily see that this n hat, the unbiased estimator, that comes out to be greater than equal to n, where small n denotes the number of ultimate units that have been included in the sample through the reference units. However, when m is greater than 1, it has not been proved that n hat is greater than equal to n. So this is not quite clear whether this n hat is going to be greater than equal to n. Now, this is the case where we are using simple random sampling without replacement in order to choose a sample of reference units. We could also, depending on the situation, use any other sampling scheme to choose a sample of reference units. And in that case, the estimate will be given by this form. Here, if you'll excuse me for a minute, I just want to pick up this call. Someone is calling repeatedly. Hello? Hello? I'm in a, huh? Okay, ask her to sit over there. I'm seminar here. Okay. Okay, I'm really sorry about that. Okay. So if we are using any other sampling scheme, then the estimator will look like this. NSS is the sampling scheme. This comes out to be of this form, where this is I is an indicator function. This is 1 if the reference unit I is in the sample, 0 otherwise. And ij given I, that is 1 if the jth ultimate unit that is connected to the ith reference unit, 0 otherwise. And pi's, these denote the inclusion probabilities in the sampling scheme. And Rj, that is the incidence count of the jth ultimate unit under probing. So this is the expression for that. So this is just a small example to understand how the method works. We have taken the same network that we have considered, where you have m equal to 5 and a sample of 3 reference units are taken, and we find the incident counts before probing and after probing, and then the calculation leads to the estimate of the size of the population of ultimate units as 6, whereas the true value of n is 8. So that is not bad, quite good, very quite close to the true value of capital N. In the case where we have no probing, in that case, we, as before, start with a random sample of reference units, and then we arrive at the induced collection of the ultimate units. Now, in this case, what we have is only the incidence count of the sampled ultimate units without probing. That is when there's no probing being done. Now, in this case, Kiranananda, as I had told you in his thesis, he has come up with an unbiased estimator of the size of the ultimate unit population. But as I have already indicated, at a later stage, it was found that this estimator is not at all a good estimator, because in many applications, n hat, that turns out to be a very large negative quantity. In some cases, it turns out to be less than the actual number of ultimate units that have been captured in the process of sampling. Now, this is how the unbiased estimator was obtained. N can be the population size can be written as summation ij. What is this ij? As we understand, this is an indicator function. This is going to be 1 if the jth ultimate unit, it is in the collection of induced ultimate units. Otherwise, it is going to be 0. And ij given I, this is 1 if the jth induced ultimate unit that is induced by the ith reference unit. And then through inclusion exclusion principle, we can write ij in this form, and accordingly we get this identity. This is n, this is equal to this expression, where ti, that gives you the number of ultimate units that have that are connected to the ith reference unit. Tik, this denotes the total number of ultimate units which are simultaneously connected to both the ith reference unit and the kth reference unit, and so on. Now, in order to obtain an unbiased estimator of n, one could do this, that is, find unbiased estimators term by term. Now, in order to do so, it is observed that for term by term estimation, the number of terms will terminate after m. That is, after the mth term, it terminates. So a condition has been imposed while using the estimator. That is, the condition is that no ultimate unit will be incident on more than m reference units. This is the condition that is used in order to get the estimate, unbiased estimate of n by using term-by-term unbiased estimation. And in this term-by-term unbiased estimation, naturally, we have to use the joint inclusion probabilities. And if the reference units have been selected using SRS WOR, then one knows the inclusion probabilities, which are given generally by pi I, pi ij, pi ijk, and so on. And with these, one can find the unbiased estimator, and that comes out to be of this form n double hat equal to summation f nf af. Now, what is this nf? This nf is the number of induced ultimate units, each having a frequency f. What do you mean by each having a frequency f? That is, this frequency f, this refers to the number of reference units to which it is connected. Okay, so this NF will denote the induced UUs, where each of these UUs, they have the frequency F. That is, they have the same number of reference units to which they are connected. And AF has an expression of this form. And this is the form of the unbiased estimator. So this is a small example using that estimator. And in this case, this is a case where we are not doing any probing. And here the frequencies that we find, we are considering the same sampled RUs, RU1, RU3, RU4, as we have done in an earlier example. And the frequencies we obtain as this: for the first induced unit, ultimate unit, it is 1, because it is connected only to RU1. For the second one, it is 2, because it is connected to RU1 and RU3. And similarly for the others we find. And then we see that for frequency 1, N1, that comes out to be 1, 2, 3. And we can calculate A1. Similarly, frequency 2, that is another value of frequency, N2, just 2 of the ultimate units. So N2 is equal to 2, and we calculate it. And we get the estimate of this as 5, as against the true value 8. Now, this N double hat that is this estimator, well, this estimator has been, or this estimate has been computed for different values of M and N using an underlying network as a bipartite diagram. And the reference units, they have been collected using SRS WOR. And many samples have been taken, and for each of the samples, the estimated value of N have been computed. And it has been seen that for some samples, this estimate of N comes out to be negative. And in many samples, the estimate comes out to be abnormally low. Like when the value of N equal to 10, there have been situations where the estimates have come out to be something like 1 or 2. So these are certain realities that one has to deal with if one is going for unbiased estimation of N. So far, these are the unbiased estimators that are available in literature. Of course, there is scope for finding some better unbiased estimator. Now, there's a heuristic approach which does not lead to any unbiased estimator of capital N, but it gives a meaningful estimate of N. So let us understand this through this example. See, we have 10 reference units, and these are the ultimate units that are connected to these reference units. Like the first 3 ultimate units, 1 to 3, are connected to reference unit 1. So this is connected to 2 as well as 1. So this has been written separately, and these are connected to 2. In this way, we get all the ultimate units. There are in all 38 ultimate units. And suppose a sample of 5 reference units are selected using simple random sampling method without replacement. Now, let us consider the sample of reference units. Suppose these are the reference units in the sample. That is RU3, 5, 9, 2, and 6. And we already know from the reference units, in fact, we can find out what are the ultimate units which are connected to that. So these are your induced ultimate units. So as we can see from here, there are in all 28 ultimate units, induced ultimate units, which means the size of the sample of the ultimate units is 28. Whereas we have started with a sample of 5 reference units. So what do we expect? We expect that this size of the population of ultimate units should be at least 28. That is our expectation. So we are going to, as I have already indicated, we are going to look for a reasonably acceptable estimate which may not be unbiased. So how do we go about it? Now, the method that is suggested is like this, that the sample network that you are getting, this is the sample network that we have. So this we treat as the complete network. So once we treat this as the complete network, we have that these are the reference units, these are the ultimate units connected to these. Now, in step 0, what we find is the average number of ultimate units connected to a reference unit in this complete network, which is basically the sample network. That is, as we note that for each, reference unit, we may have a number of ultimate units connected to it. So we consider the number of ultimate units connected to each of these reference units in the complete network, which is, as I'll repeat, is basically the sample network. And we find the average number of ultimate units connected to a reference unit. Now, for the example that we are considering, that is, this is the complete network we are considering now. So here, this average comes out to be 8.1, which means we can say approximately 8 induced UUs corresponding to a reference unit. That is corresponding to each of this reference, 5 reference units. So this is the average number of average number of induced ultimate units connected to a reference unit. Now, in step 1, what we do is, from the complete network, which is the sample network, we select one reference unit. Since there are 5 reference units, naturally, there are 5 choices. Now, once we select a reference unit, we then, from the remaining 4, we select another reference unit. So there are 4 ways in which we can do that. So in all, we have 20 ordered pairs of reference units. Okay. And from these 20 ordered pairs, what we are doing is we are selecting just one pair. Suppose we have selected RU3, RU5. Okay. So now we count the number of ultimate units connected to RU3, the first one in this ordered pair. And that comes out to be 7. Okay. So that is 7. Next, what we do, we look at the second reference unit in this pair and we count the additional number of induced ultimate units that are connected to RU5 but are not connected to RU3, and that comes out to be 8. And this is called the increment of level 1. So when we are taking a pair of reference units, this is our level 1, and we count the increment of this level as the additional number of induced UUs which are connected to RU5 but not to RU3. Now, as I said, we have 20 such ordered pairs. So these are all the 20 ordered pairs. And for each of these pairs, we can count the increment. We get these as the increments. Once we have obtained the increments, we can obtain the frequency distribution of the increments. So this gives you the frequency distribution of the increments, from which we get the mean increment to be 6.75. Now, increment should be an integer, so this can be taken to be approximately equal to 7. Step 2, that is level, that is level 2. So in this case, we are going to select an ordered triplet of RUs from the complete network, which is basically your sample network. So here we can have 60 possible triplets, and we say we consider or we select one such triplet. Say this is RU3, RU5, RU9. Say this is the one. Okay, then the increment at level 2, that will be the additional ultimate units which are connected to RU9 but are not connected to RU3 or RU5. Now, for all these 60 triplets, we calculate these increments, and then we find the average increment, which comes out to be 5.43, which is approximately 5, you can see. Step 3, in this case, we select 4 RUs, that is reference units. Now, in this case, what happens is that when we are considering a 4th reference unit, then after we have selected the first 3, we find that that will not cause the increment to be dependent on the order in which we have selected those first 3 reference units. So now we need not consider ordering of the reference units in the sample. We just consider firstly the first 3 reference units that we have selected. We consider the unordered choices. And we have in all 5C3 unordered choices, that is 10 choices. Now, once we have selected 3, then next we select the 4th one from the remaining 2. So that can be done in 2 ways. And therefore, in all, the number of choices we have is 10 into 2, that is 20. Now, for these 20 selections, possible selections, we can get the increments. We get 20 increments, and the average or the mean increment comes out to be 4.5. Next, we move to step 4, and now we consider 5 reference units. Now, for that, we first collect 4 reference units and then the 5th one, which is remaining. Here again, the first 4 reference units that we are collecting, that will not have any effect on the additional increment. So we can just consider the unordered choices. That is going to be 5. And the remaining one will be the 5th one we are choosing. So in all, we have 5 such combinations. And for each of them, we calculate we find the increment values. And we find the average of the increment values. And that comes out to be 3.5. Now we can have the array distribution of the increments at different levels. We have considered 4 levels, 1, 2, 3, 4, where the 4th one has included 5 of the selected RUs. And these are the frequency values all the possible frequency, I'm sorry, not the frequency, increment values that we have come across. And this, the last column gives the mean increment at the different levels. And these are the frequencies of the increments at each level. Okay, and these are the mean one. What do we do? See over here, we find that there seems to be a relationship between the level and the mean increment, so that we can think of a regression where this can be, the mean can be estimated from the level. Further, to get the variance, we need the array distributions, each of these array distributions. And these seem to be quite distant, and therefore we can consider heteroscedastic regression over here. So regression of y on x is considered, and heteroscedastic regression is considered over here. Now we note that in the sample, 5 of the RUs had been selected. And in all, there were 10 RUs, which means that 5 RUs are left out. So if we want to estimate n, we need projection of y bar for all the remaining RUs. That is, our projection should cover x equal to 9, because up to the 5th RUs that in the sample, we have considered levels 1 to 4. So we need 5 more levels. So our projection should cover x equal to 9. And from there, we can predict the value of n. So this is the line, fitted line, rather the regression line, and generalized least square method give these as the values of alpha and beta. And then for x equal to 6, 7, 8, and 9, we can estimate the values of y bar. And not 6, 7, 8, 9. It is 5, 6, 7, 8, 9. I'm sorry, I've missed it. So, well, these are the values of x, 5, 6, 7, 8, 9. These are the predicted values of y, which when rounded will give you 2, 1, 0, 0, 0. Okay. Now, how are we going to combine all this? So at level 1, the average number of ultimate units corresponding to each reference unit was 8, and the average increment was 7. So to that average number of ultimate units per reference unit, if we add the additional units, that is the increment, then we are getting 15, because these the average increment that we are getting, that corresponds to ultimate units which are not already in the average induced ultimate units. Okay, so we add them, that comes out to be 15. At levels 2, we are getting increments on the the average increment as 5. So this 15, 5 more ultimate units, so 20. At level 3, average increment is 5. So the number of ultimate units comes out to be 20 plus 4, 24. At level 4, in the average increment is 3. So the number of induced ultimate units, that is pushed up to 27. Now, for the other levels, we have already predicted the value of y, that is the average increments. So we go on adding those, 27 plus 2 plus 1 plus 0, 0, 0. That comes out to be 30. And so we get the predicted value of n as 30 as against the true value, which was 38. Yes, it was 38. Now, this does not really give you an unbiased estimator of n, but the method does give you a meaningful estimator in the sense that here, the unlike in the case of your unbiased estimation, where we found that in some situations we can have the estimated value of n to be very large negative quantity. So this is not possible over here. And secondly, we had that in some situations, the estimated value came out to be less than the ultimate units or the number of ultimate units in the sample. That is also not true over here. That will not happen, ever happen over here. So this seems to be a very meaningful estimate of the population size, that is size of the population of ultimate units. So these are the references for the work. Thank you.
Thank you, madam, for your nice presentation. Now, the session is open for all for taking questions and comments. Let's over to the audience to deliver some questions and comments to the speaker. Please.
Somrat, can you hear me?
Yes, sir. Yes, sir.
Good. This is Bimal Sinha from the University of Maryland, Baltimore County. Manisha,
Yes, Bimalda.
I enjoyed your presentation very much. I have a very basic question. Given that unbiasedness in this
Yes,
particular scenario leads to some problems, is it
yes,
possible that we can go away with the requirement of unbiasedness and just look at the problem from a likelihood point of view? After all, there's a data generation process. Hopefully, that will lead to a likelihood. And I can assume a prior on capital N because there's
yes,
obvious constraint. Capital N is bigger than small n, or at least the observed number of, or the expected number of distinct units. So
yes,
with a natural lower bound on capital N, we can have a prior and we can look at the posterior distribution of capital, and that will capture the whole scenario given the data. And from there, we can compute on whatever you want to compute. Is that a reasonable approach, and has it been addressed?
No, it has not been addressed. I think that would be a good approach. As far as
I
I
know
know,
that.
that has not been addressed.
Good. I know that there are about, I don't know, maybe about more than 60 attendees. So for some of the budding PhD research scholars, this should be a good problem. And of course, Dr. Pal, Monisha Pal, and Dr. Vikas Sinha, they'll be ready to help. They'll be ready to contribute. Am I right?
Yes, of course, Bimalda.
Good.
And I should add that, well, I have been inspired to, what to say, talk about this topic by Vikashta. Vikashta has really uh, exposed me to this type of estimation. You
Yes,
know,
yes, yeah, yeah. I know that, yeah. Very nice. Nice presentation, Monisha. Good.
thank you, Bimalda.
Thanks,
Thank you.
Manisha, for this very interesting presentation. It is
Thank
quite
you.
interesting. The only, so there's a point I would raise is nothing concerning what you presented. It's slightly beyond this, but then this is the requirement in practice occasionally, not in all situations, where you try to apply network sampling, for example, the total number of reference units, and that way a frame, in case you want to have a sample of reference units, sometimes may not be available in real life situations in some contexts, not in all. So in those rare situations which are quite difficult, we may have to think of something beyond whatever you presented. I don't know, because in the sense that we don't have a frame of all the reference units which
Yes,
are visited by the ultimate units, and we
yes,
can't have a sample in the usual sense of the term. These are real life problems which were once presented by the government of India to the National Statistical System here, and
okay.
there could not be any satisfactory answer. But anyway, whatever you said is quite interesting and should be definitely inspiring our research students and successive generations of students. Thank you. Thank you.
Thank you, sir.
Any comments, suggestion from others?
Nitish, sir.
Sir, kindly unmute your mic, sir.
Manisha, very nice talk. Bimalda said, Shama Prasad said.
Thank you, Nitish,
I
sir.
I have a very minor question, comment, whatever. Once you go to the reference unit,
Yes,
even if there is a frame and so on, so Shama Prasad's point is well taken. But even
yes,
if the frame is there for reference units,
yes,
some of these connections
yes,
you may not be able to readily observe because people don't necessarily give you the information what is connected to what, because they always doubt statisticians that you are going to use these connections, if
yes.
any, for something else, and you will discover something else that may penalize them in some sense. So that issue is always there. So even if there is a frame, and suppose I go to a reference unit and try to get the connections, the network graph, I may not be able to construct it, then what?
Okay. So that does pose some difficulty because the whole thing, all the methods that I have talked about over here, these methods, they assume that the reference units, the sampled reference units will give you all information about the ultimate units that are connected to that reference unit. So in case it is not the case, in that case, I presume that we have to think of or estimate some probability of not getting the correct information from them and try to include that in the estimation procedure.
Right, right. So some more work needs to be done by
Yes.
uh, the incoming scholars and so on. So that would be nice. Nice to see you, Vimalda.
Because would you like to make some observations?
Yes.
Yeah, I would like to hear.
Yeah, I will make some observations.
Yes,
Let me
please.
start with Nitish. So what we have done, as you can see, we are assuming that from the reference units, we can extract information on the ultimate units as much as possible. Also going beyond asking them, going through probing so that something more can come out of the ultimate units. Now, whatever you said, if that information is not available, then possibly we have to dig into other methods where the probing is not working, but we can possibly get a small network and extract information from them. Anyway, this is a triennial, and the next triennial will be 3 years hence. And we have enough time to dig into this problem and come up with some nice solution.
I'm sure you will get some many
Yeah.
things done. Thank you.
But this problem really, so yeah, I'm talking about maybe about 20, 25 years back. We had our ISI colleagues, Pulokesh Maiti and Manoranjan Pal. They came to me saying that they were engaged in a tourist survey in Digha and Puri area, and it was being conducted by Professor Deroy. He was the ultimate person, and then they were in a team and working. So that is the time when I got into this idea of probing and got into the formula that Manisha showed.
And then Pulokesh got into the literature of this Kiranandan PhD thesis, and Kiranandan's work was really out of nowhere how he came up with that example, that expression for the unbiased estimate of capital N, that itself was very amazing. But anyway, we could, along with Somin Sengupta, we could dig into the problem and then we could see how the derivation is coming. So we could do something, but still that undesirable feature of unbiased estimate becoming negative and becoming too low, that was still bothering me. So when I visited ISI Delhi, not Delhi, ISI Bangalore, over there we had a student Padmavar who worked with T.J. Rao in sample survey in ISI Calcutta. I asked Padmavar, would you be interested? He said yes. Then we started digging into this regression matter. So we take a network and we pretend that this is the complete network. And then we go on subsampling from this, as Manisha explained very well, of different sizes, and then adding, so that we get a sense of regression. So then we could possibly go ahead and then do the data analysis. And this part we could do, and we had some projection, and on the whole it was okay. So that is the history, how it goes during the last 20, 25 years. So Padmavat took it up in Bangalore, and then we had a paper that came out in JISA, Journal of Indian Statistical Association. So our first paper was in one of the triennials, the first triennial maybe, because that is when Bimal Sinha and Sujit Basu, they were the joint editors of a Narosa publication. And in that our paper, me, Pulukesh Maiti and Manoranjan Pal, our paper came out and we talked about the probing matter. That is how the history goes anyway.
Because I have a question for you.
Yeah.
When you look at that dissertation, and then of course there are some negative features, is it possible to, at least, given that it was a great idea back then, is it possible that you could fix it so that we give up unbiasedness, but maybe add a little bit of bias, but otherwise the estimate is okay?
That is what I'm saying, that we took up the problem and we immediately abandoned the criterion of unbiasedness. We thought it should be reasonable, acceptable. Acceptable, that means it should be greater than equal to the minimum, the sample size already obtained through the data. The sample size means the number of ultimate units already captured through the data. So our estimate should at least be that much, and then there should be a reasonable estimate.
I understand, but but the point is, I understand, but the point is, if you look at the proof of the unbiasedness, whatever it was suggested in the dissertation now, is it possible that we could, you could just tweak it a little bit so that, we give up unbiasedness, but otherwise, it was a great idea after all. And nobody thought about it. So is it possible? Was it possible to do something with that estimate? Maybe changing a little bit of, rather than giving it something completely.
One obvious thing could be truncation. So capital N hat is equal to small n if it is less than small n. Otherwise, what one natural immediately you make into a truncated estimator. That we did not find very exciting. We thought, okay, so what we have done, we have given a proof of this result in our own way, and we have given the unbiased estimate of a general population mean or population total rather than just the counting.
Okay.
So we had to go a long way.
Okay. All right. Thank you.
Mm-hmm. Manisha, I enjoyed your presentation.
Thank you,
It is a difficult topic, but you did justice to the topic. Yes.
Next, if anyone really interested to make some questions, comments, kind.
Comrade, I have not a question, but I'm just curious to know. I see that there are about 44, 45 attendees now. Who are these, interested listeners? Are they all from Calcutta University alumni or some close by people or what? I have no idea most of them where they are from. Do you know? I'm just curious to know.
Yes, I have just a little bit idea about that. A maximum of us from related to the CSA, Calcutta Statistical Association.
Good.
Some
Okay, that's
of the students and the scholars, some scholars from Department of Statistics, University of Calcutta, and from others also.
good.
That's the audience. That's from the audience side.
Good. প্রফেসর মুখার্জি, খুব ভালো লাগলো স্যার আপনাকে দেখে। ভালো থাকবেন, প্রণাম নেবেন।
ভালো থেকো তোমরা সকলে। তুমি তো পুজোর সময় আসবে।
জানি না, ঠিক নেই এখনো। এলে অবশ্যই দেখা হবে।
নিশ্চয়ই, নিশ্চয়ই। সবাই ভালো থাকলে ভালো লাগে।
নিশ্চয়ই।